Thank you, Maria. So contrary to all my fellow speakers that they have presented well-established tools, actually it's the first time that we are presenting SolarOPS, which is a completely brand new tool. And I'm quite happy to present it on behalf of the whole team. This is the standard disclaimer. So a few words about TotalEnergies and our involvement in renewables. Maybe you know it as an oil and gas major, but actually TotalEnergies is gradually transitioning to become a low carbon energy company, utilizing mostly solar and wind. By the end of 2022, we had 17 gigawatts worth of assets in wind and PV. And according to the pipeline, we will have 35 gigawatts by 2025 and 100 gigawatts by 2030. And this will allow us to fulfill our ambition to become one of the first top producers of renewable energies in the world. Also, for that, we have a strong focus on renewables R&D, and this is manifested by a large number of relevant patents. At the core of this effort, we have the power R&D, which is consisted by 4 programs covering the entire electricity value chain, namely wind, hybrid and storage, solar, and DER. And whatever I'm about to present you, it's part of the solar program. So, okay, let's come to the SolarOPS itself. What is SolarOPS? So it is an internally developed PV performance simulation tool which is used complementary with PVSys to address complex scenarios where PVSys has some limitations, to offer increased predictive accuracy and component optimization, to interconnect SolarOPS with other internally developed frameworks for large-scale optimization within TotalEnergies. A few words about the background and the technical specification. It's Python-based. It makes use of radically redesigned libraries from the PVPMC community and Radiance. It is accessible via a dedicated web app, but it's only internally accessible, of course. Due to the ray tracing that it utilizes, it's really computationally intensive, so we are deploying our tool either to Azure Cloud or in some cases to TotalEnergies HPC infrastructure. And as you will see, it's quite flexible because the users can opt either between the rigorous ray tracing or the fast PVSys-alike or PVLib view factor optical models. We're working in a way to develop on demand based on requests that are coming from our internal stakeholders. And we are trying to enhance the confidence on our tool, making continuous validation using meteo and performance data from our own pilot sites. A few words about the intended use. So as I discussed, it's only intended for internal usage, and we have 2 focus. One is to support TotalEnergies solar R&D activities and also to conduct studies on demand for specific technical problems. A few words about the key features. So we have 3 modes of operation, the well-known view factor, and 2 types of ray tracing, the faster line scan and the more rigorous grid scan, which is taking place at cell level. We are able to incorporate blue sky data coming from post-processing of MODIS obtained data. And also we can define spatially the albedo, both for view factor and ray tracing. Also, we have flexible ways to define soiling, either by means of time series, cleaning schedule, and the classic constant way of defining soiling. One other important feature, which is specifically useful for vertically mounted modules that they are used in agrivoltaics, is the fact that we can specify different high bifaciality side on the upper and the lower side of the same module row, which allow us to do this simulation just at 1 stroke. Also, we can create maps of the ground irradiance distribution, which is specifically useful for agri-PV applications. And we are working on the automation of design optimization and the uncertainty propagation. A few words about validation. Of course, continuous validation is at the heart of what we are doing, and we are using data coming from our own test sites. Actually, we have several test sites that they are either live, active, or they are about to become live very, very soon. I will just illustrate 3 indicative test sites that we are using mostly for the assessment of our ray tracing capabilities. So we have 1 site in France and 2 sites in Qatar. which they represent completely different climate conditions. The site in France incorporates next to sun modules, and it's about agrivoltaics, so they are vertical modules, while in Curie we have single-axis tracked bifacial modules and fixed-tilt bifacial modules. From the rating itself, you can see that they are very small configurations, which make also the modeling more challenging and more interesting for us. So on the diagrams on the right, you can see the relative bias and the daily normalized RMSC comparison versus PVCs. So as you can see, ray tracing outperforms PVCs for small installations. This makes sense because ray tracing, of course, is not suffering from edge effects. And also we have a way more detailed way to introduce soiling and albedo as time series. We have a much more detailed racking configuration and so on. Also, we see that the difference on the bias is more pronounced on Agri-PV vertical, probably due to the higher sensitivity from the ground albedo. On the other side of the spectrum, when we use view factor for much larger installations, and we compare it with PVCs, we see that always the difference, the bias between SolarOPS view factor and PVCs is in the order of less than 1%, which is completely normal, as more or less we are utilizing the same types of models. Okay, the next part is some use cases. The first one is about PV production in agrivoltaic systems. So the motivation is to combine PV energy generation and crop production by embedding PV systems on agricultural land. The use case is, this specific use case is vertically mounted next to sun systems that they are installed within the crops, and they are highly sensitive to the crop reflectivity. And the reflectivity itself, or albedo, varies throughout the crop growth cycle. The methodology that we are using is to use ray tracing to include the detailed structure, and we are adding zones of different albedo, crops and no crops. And then we are using albedo as time series, and we have two different ray tracing strategies, line scan and grid scan. And here you can see results from the more rigorous and more time-consuming grid scan approach. And every small square that you see represents an actual cell on the whole module array. The next part discusses the ground shading distribution. In this case, again, we are talking about Agri-PV, and the idea behind it is that the PV modules affect the irradiance distribution on the ground, which in turn can affect the available photosynthetically active radiation, which is crucial for the plant's photosynthesis. The idea now is to use ground shading patterns due to the different PV technologies and to assess them, compare them, and see what is the outcome for different geometric configurations and for different locations. The methodology that we are using is, again, focusing on ray tracing, and we are calculating, so we are actually creating, we arrange different sensors on the ground, then we get hourly ground irradiance maps, and then with the post-processing, we can aggregate them and create monthly, yearly, or whatever other type of aggregated values. And this is just a snapshot, a comparative snapshot from monthly productions for 3 different types of configurations. And why it is important is that because having this information for the monthly ground irradiance distribution, we can provide guidance to the farmers for the optimal placement of the crops based on the available light for photosynthesis, and in general to obtain insights on the impact of different configurations on shading patterns. One other interesting use case is the bifacial gain enhancement via geotextiles. So what is the idea behind that? Behind it is that we can enhance the bifacial gain by using high albedo geotextiles. But the idea is not just to flatly put this expensive material everywhere, but to try to find the optimal placement and width of the geotextile under various conditions to have the lowest LCOE. The methodology here actually utilizes both ray tracing and view factor, but we are focusing on the view factor, which is much faster and can enable this kind of large-scale optimization studies. So what we are doing, we are starting with the ray tracing simulations, which are supposed to be more accurate, and we can place the areas of different albedo with geotextile and no geotextile. And then we make a comparison versus experimental data that we have. And we see that if we increase the number of modules, then gradually the ray tracing and the view factor start to become, to have the same values, they converge. And this allows us to create these kind of diagrams of position dependence of sensitivity, both for tracking and fixed tilt, which can allow us to optimally place our geotextiles. And for that, you can find way more information on the upcoming presentation in IEEE PVSec by our colleague Niels Harder, which will discuss exactly this topic. One other interesting use case, which is under development and currently exclusively used within Solar R&D, so we are not using it with our business line and units, is the optimization and uncertainty propagation. So the idea here is to reduce the time for design optimization of a power plant by means of statistical approaches and automation, and also to make a detailed estimation of the uncertainty based on the propagation of the uncertainties of the individual inputs. The use case here is the design optimization for different KPIs, either production, LCOE, and so on, and the propagation of the uncertainties. The methodology is that we are creating a workflow that combines SolarOPS with an advanced statistical framework which was developed several years ago within Total, but for a completely different purpose, which is oil reservoir exploration projects. So practically, it's a two-step approach where first we conduct optimization, and then based on the optimized scenario, we are conducting uncertainty propagation estimate. Unfortunately, I cannot go into too many details, but what I can say is that the potential outputs of this framework have to do with the ranking of the optimal scenarios based on different KPIs, to create Pareto diagrams showing the impact of the individual parameters on the targeted KPI, and also to create probability distributions of the targeted KPI based on the uncertainty propagation framework. The last use case is about carports and how we can optimize the design. So carports are, you can see them more and more, but in this case, we are about to use bifacial modules, which makes the overall modeling even more challenging, both in terms of optics and electrical mismatch. So in this case, we are modeling a bifacial carport in VC France, and we assess also the impact of the seasonality and cars that they are parking underneath the parking, which they create a spatially and temporally inhomogeneous light distribution. In this case, of course, we are using ray tracing, and we have two different ways to introduce the structure, either in a programmatic way or also with a special, let's say, arrangement that we have to create the structure via a CAD file. And for that, we are using a similar approach to a tutorial from NREL. All these simulations are focusing only on the optical part, and we have some indicative results. It's really preliminary work at this time, but we were able to make some comparative studies on the impact of having cars or not having cars during winter or during summertime, and also the impact of having different pitch or distance between the different carports. And that brings me to the outlook and the perspective work. So to sum up, SolarOPS, which made its debut today, is a PV system performance simulation software developed and used internally at TotalEnergy for the modeling of complex cases in conjunction with PVSys. The ray tracing and view factor optical models are available on demand, and there are several new features that they have been developed to address internal requests. We are leveraging our own pilot site for the validation, and as discussed, the ray tracing has increased predictive accuracy versus PVSys for small installations, while for large UPP installations, the SolarOPS view factor and PVSys yield almost identical results. And I showcased some different use cases. There is a lot of things to be done as it's a relatively new tool. We want to increase the flexibility. We want to model uneven terrain, to automatically introduce CAD files, because currently we have a tedious methodology to do that. We want to expand our validation for more test sites and for a larger variety of conditions and configurations. And for that, a lot of new test sites will become live very, very soon. And also, we want to explore various strategies to minimize the runtime for the time-consuming ray tracing, and also to conduct enhancements on the thermal electrical part. And also in this link, there is this report about our activities on renewables. And with that, I would like to thank you for your attention and time.